Hey everybody, this is Larry. This is day 8 of the August Leetcode Daily Challenge. Hit the like button, hit the subscribe button. Join me on Discord. This was a hard problem, so let me know what you think on ranked transform of a matrix. And if you see me already with the problem opened up, it's usually because I solved it, but it took way too long, so I'm doing the explanation in front. This one I actually am going to do things a little bit differently. I actually did review my notes after solving it, and I'm not going to cheat you. I will show you how I solved it live later in the video, but I actually solved this problem during the contest about 9 or 10 months ago, and I actually did remember this. I actually didn't remember all the details, but as I kind of went through it, I remembered more and more. And this is maybe where practice and experience come in, even though this is the exact same problem, and I did this during the contest or after the contest, but you know, like I'm not trying to memorize problems. I'm not trying to memorize at all. I'm trying to learn things, right? So sometimes it will take a few times to stick. And in this case, in the original contest, or after the contest plus extra time, it took me about 90 minutes, maybe a little bit more to finish. Today, it took me about half an hour or so. Still a long time. I'm not going to bore you with all the details, but you know, I'll have a link below if you want to watch that video to kind of see how I did it during the contest. But that said, so reviewing those notes, and this is something that I do on my old code, and just like kind of see how the older Larry thought, and solve that problem. So it turns out that my code for today is very similar to how I solved it there. So I'm going to just edit that in next. So you can kind of see that. So just to be clear, I have a long explanation for my contest code, which is a little bit different than my code here, but mostly the same, to be honest. Actually, yeah, mostly the same, to be honest, and yeah. So I'm just going to play that video back for you because even the explanation was like half an hour. So it's a very hard problem. Yeah. And I think the only thing that I'm missing from that video is I didn't do the complexity right, or I just kind of hand waved over it at the end. But the short answer is that the complexity is going to be n squared log n, time, and all of n squared space. I actually go over this in my today's solve video, so all the way at the end of the video I have some complexity analysis there, so maybe skip ahead to that if you want to be doing this if you want to see the analysis. But I'm just going to go over this code really quickly, and then I will go into the more detailed explanation, and then after that you can see how I solved it today, even though which is what I typed here, even though the code is very similar, almost like kind of weird that it is that similar. But okay, so yeah, and I drew graphs and everything, so hopefully, you know, that's a good enough thing. But the short answer is topological sort. You can think about this problem as dependency graphs, as for example, if you have, now let's just say you have a one-dimensional array, then you know how to solve it, right? I would also say that this makes it like, you know, a trickier problem. But for example, you have this, and I actually go over this in the explanation as well, but the short answer with the topological sort is to try to figure out the dependency graph, and then after that you do a topological sort and then number them in order. So in this case, you know, for example, it's easy to think about, have 2 pointing to 1, 3 pointing to 2, 4 pointing to 3, and 5 pointing to 4. So that's basically, you know, how you do the graph. And then after that, yeah. And the tricky part about this problem is that I'm using union find. And the reason why I'm using union find is that for 2, you can, okay, let's bring back some graphs. But you can imagine that, actually, let me take a matrix here. Whatever. Let's just do another one then, right? Let's say in this case, right? The two ones are actually not related, and they could even have different values. However, two numbers have to have the same value if they're in the same row in the column and have the same value, right? So that means that if, for example, in this case, let's say actually I moved the one here. Right now they're not correlated. They do not need to have the same value. However, if I change this 9 to a 1, then all these 3 ones have to have the same value. So that means that we have to process them at the same time, and that's basically what I did here. And I kind of connected all the ones in this case using connected components, in which there are a couple of ways to do it. The way that I did it is with union find. So yeah, so this right here is just a 2-dimensional union find setup. I'm not going to go over that too deeply today because, you know, union find could be a lecture or two in class. So it's a very big long topic, so I'm going to just keep it short. And then next, this is basically me trying to figure out how to dedupe or how to combine the same numbers, right? And the reason why I did it this funky way is that for example, if you do a naive search type algorithm, let's say you have, you know, just 1 1 1 1 1 1 1 1 1 1 1, right? Let's say you have this thing, which is taking some time to come up on screen for some reason. Okay, I don't know why my browser is lagging so much. But in this case, if you do a naive way of combining them, note that there's n. Let's put, you know, let's say there's x numbers here, then there are x square number of pairings. So if you kind of do this naively, you are going to, you know, you're going to mix up a little bit. And also then you ask yourself, okay, what if you have to go down and then you go do it again? So there are definitely a lot of ways to do this incorrectly. So that is why, and you know, I want to make sure that it runs as fast as possible. And that's why I did the dedupe this way. And how did I do the dedupe? I basically put all the numbers that share, or all the cells that share a number, I put it in a list. And then for each list, I look at all the positions. These are basically just we build out all the positions of all the, for example, for all the 1s, for all the 2s, for all the 3s, and so forth. And then now we put all the positions. And notice that for this problem, we only combine stuff if they're next to each other. So, or if they're on the same row or the same column. And two things have the same row or column if after we sort them, they're next to each other. You could do another hashing type thing as well, but this is the way that I did it. Yeah. And then lastly, I basically just keep track of all the parents, meaning for each component, I put it into a list so that I have a list of components, and then I make sure that I put it in an event. So this is the order that we parse them. Later, we sort the events, and then we just basically, for each event, for each component, we look at all the cells, and then for all the cells, we try to figure out what is the max number that is in the same row or columns as that cell, and then now we populate all the children all together. So yeah, so this is going to be n squared. This is going to be n squared log n for the sorting. This is actually n squared log n squared, but you know that goes down to n squared log n. And here, the sorting here is also averse n squared log n. So yeah, so that's basically the reason that we have this. Yeah. That's all I have for this one, for the really short explanation. Again, if that wasn't detailed enough for you, I have a longer explanation coming up. So stay tuned, watch that. It's a little bit longer, but it's a little bit more detailed, and I even drew a lot of diagrams. So let me know how let me know how that goes. And then after that, you can watch me solve a live during the contest today. Yeah, today is a very confusing video day, but this is a very confusing and hard problem. I think the idea is topological sort, and that in itself is straightforward, but the implementation and the edge cases and therefore requiring connected components, it's kind of hard if you ask me. So definitely slow it down, maybe watch it a couple of times or do whatever you need to do. But yeah, anyway, that's it for me for the current Larry for today. Have a great night, and you could watch the explanation next. Hey everybody, this is Larry. This is me going over Q4 of the recent contest, Rank Transform of a Matrix. Sadly, to be honest, I didn't solve this during the contest. I solved this about like 10 minutes afterwards with some motivation. You could watch me solve this live during the contest and also afterwards, after the explanation part. Hit the like button, hit the subscribe button, join me on Discord, let me know what you think, let me know your questions. I appreciate your questions, because the more questions you have, the more I know to answer them next time. And also I'll answer it this time as well, of course. Anyway, so this one, for me, this one is very tricky. And I'm going to bring up Point Bush for a quick I'm going to, so basically I'm going to go over two cases, not two cases, but I'm going to go over a different problem first. Not a different problem, just like just like a easier version of the problem, say, right? So let's say I have a easier version of the problem where all the numbers are unique, right? Well, if all the numbers are unique, then we can, this becomes a lot easier. Let's say we have a matrix. Let's actually add a couple more boxes, and the numbers really don't matter per se because they're unique. But basically, you can kind of think of it this way, right? So we could look at each cell as a node, and for each node, we have a pointer that goes from, you can think about it as each node, and that if a number is smaller than the previous number or another number on the same row or column, then you have a node, you have an edge from that node, right? So for example, let me use a color that is not, that's a little bit stand out. So basically, for example, you have 1, you have 2, you have 3, you have 7, you have 6, right? Something like that. And also let's just fill out the rows a little bit, or the column for one of them, something like that. Right. So the idea behind here is that, okay, so you have a matrix that's filled out. So we just have to draw these edges. So for example, in this case, 2 is bigger than 1. So you draw an edge here. 3 is bigger than 2. And also 3 is bigger than 1. 7 is bigger than all these numbers. But you get the point here, right? And also 7 is bigger than this 1. 7 is also bigger than this 2. And 7 is bigger than this 5 and 4. Though this is, you could keep on drawing. I mean, you get the idea here, right? So the idea behind this is that now we create an edge where essentially a dependency graph. Because basically the way that I was thinking about it is that in this case, now that we have this dependency graph, and it's kind of intuitive, which is that to say in English, to articulate it in English, which is that you always want to do the 1 before the 2 before the 3, the 3 before the 7, and so forth, right? In this case, in the same row and column. And if you think about it that way, well, then you could also think about it in another way, right? Which is that 2 depends on the 1 to finish first before it can go. 3 depends on the 1 before it could go, and 3 also depends on the 2 before it could go. 7 depends on the 3, the 2, and the 1, right? So that's kind of a dependency graph, and if this rings a bell to you, then good. And if not, that's okay. This is why we're here. This is why we practice. I mean, I didn't solve this problem during the contest, right? So I'm not trying to shade, but basically after that, then you've got to the problem becomes a little bit more familiar in that it is just topological sort, right? What is topological sort? So topological sort just allows you to kind of, for each node, we only process a node when there's no edges looking out at it, right? Going out, right? and what I mean by that is that if you look at this graph right now that I drew, so first, well, first we're going to draw let me change the color again. First we're going to do this one, and we're just looking at rows for now. We'll generalize it a little bit. We'll solve it as 1 because, well, because 1 has no outgoing edges, right? This is very basic topological sort. I recommend you practice up on that if that's not understanding, because I don't want to spend too much time on the topological sort portion, because I'll just say that this is a prerequisite, right? But we do the 1, and then after that, so if this goes by too fast, that may be why. But yeah, and then next we do the 2, because now after you you process 1, 2 is good, right? Because now 2 has no edges going out because it only has an edge pointing to number 1, but that didn't count, right? So, and so forth. And now you could get the intuition that when you do a topological sort, so that's one part. And then the other part is, how do you label them, right? Well, when you label them when for a given cell, let's say 7, right? So now we you may notice that this 7 also has edges pointing downwards, as well as to the left and to the right. I didn't draw that one, but so it has a lot of edges going left, right, up, down, right? Because 7 is a big number. And so by the time it's done, you can just look at the maximum number on the row or the maximum number on the column, and then just make sure that this is the biggest number after those numbers. So that's how you process each node. I'm gonna go over my code real quick. So in the case where so basically for each row I just keep track of the max number, and then for each max number I keep track of the rank, and I update the rank afterwards. This code may look a little bit weird, so I'll explain it a little bit. Okay, so that is how you would solve it if there was no unique numbers, right? And that would be pretty straightforward. Well, it was still hard because it still took me about an hour of implementation, maybe a little bit less. It's just that I was having issues with typing. No, it took me probably like half an hour just to kind of get all of it right, because there are some optimizations that you have to do, even though this is the core concept. So for me, this was a really tricky implementation problem, though it turned out that there was a thing that I didn't consider, which made it interesting. But it's implementation problem because so let's say we want to draw these edges, right? Looking at the same graph, we're looking at 7. 7 has a lot of edges, if you could tell. In fact, 7, the largest number in the graph, in this case 7, say, will have, if you have, given that n is 500 and rows is also 500, so each cell could have up to 500 plus 500 edges, right? It's not quite like that, but because not every number can be the biggest number. But if you do some like n choose 2 math, right, like n square math, that still adds up. And given that n is equal to 500, that's gonna be too slow, right? So basically, what you have to do instead in this case is, instead of all these edges, okay, well, it's not erasing all these edges for me. So let's just pretend all the edges are erased. Let's just at least clear up a little bit. Okay. So let's say we cleared up all these edges. Okay, let's just say there's no edges, and I'll use another color. We'll use green. Let's say there's no more edges, right? But one thing you can note is that if 7 7 depends on 1, 7 depends on 2, 7 depends on 3, right? Well, that's a lot of edges. But we also know that in this case, that we don't need, you think about taking a class, right? Like, and that's how I always think about topological sort and dependency graphs. I think about taking classes in college or something like that. You have to take, let's say you have to take a, I don't know, yeah, you have to take quantum mechanics, and quantum mechanics requires, well, physics 1, physics 2, physics 3, and physics 4 or something like that, right? Which makes sense because quantum mechanics is hard. But you know, like, but if you ever look at your course book, they wouldn't literally list all these courses, right? So and I think that in an intuitive way, you know where I'm going to go with this, which is that you can just, if in this case, knowing that 3 depends on 2 and 2 depends on 1, and because this is not an arbitrary dependency graph, this is a dependency graph on just numbers, right? So you know that on numbers, if A is bigger than B and B is bigger than C, then A is bigger than C, right? So this is the transitive property, and because there is transitive property on ordering of this, so what we can do is actually, instead of drawing all these edges, and there'll be n square edges, because then choose 2 edges, right, for each row, and that just becomes way too big. You can actually just look from 7, you point at 3, actually, technically speaking, 7 point at 6, 6 point at 3, 3 point at 2, 2 point at 1, right? So that's kind of how I would think about this. And then once you do that, it becomes like a linked list, essentially, and you have n edges per row, right? And because of that, that's just going to be also n square in total, because there's only n per row and n columns, I guess, say. So it'll be n times 2n, so it'll be 2 times n squared number of edges instead. So that is an optimization that is needed for this problem as well. So there are other things that you have to do with it, but yeah. So let's say now that this is unique. This is unique, and this is how you would solve the problem, because now you have this dependency graph, and I took a long time implementing it, but yeah. Now that you have this thing, so you can do a topological sort on it, and if all the values are unique, that's pretty much all you have to do, and that's how my first code works. So I had a couple of wrong answers during the contest. Oops, not this one. So I did do this in the first one, but I actually end up not going this well, though. We'll go over why this is the case. But yeah, I keep track of out degree, in degree, and stuff like that. But the problem is actually, and I will draw another one because there's a good edge case here. But the problem is non-unique numbers, duplicate numbers. How do you handle them, right? So I did not handle this well. But oops, let's go with black for now. We don't have to draw that many cells, I don't think. But you know, let's say we have yeah, let's say we have 0 here, 0 here, you know, I don't know, it doesn't matter here. -1, -2, 3, doesn't really matter as much as well. So it doesn't, right? So let's say this is our very rough matrix, right? Because the algorithm will mostly still work with it will mostly still work with topological sort, but now the problem is it's not true, it turns out, right? So basically what happens is that, okay, let's just draw an edge for this node here, right? Or edges for this row and column for this thing. So 0 points at 2, as we said, 3 points at 2, 2 points at 0, 3 points at 2, 4 points at 3, 0 points at 2, or 2 points at 0, sorry. I keep on saying it backwards, and so forth, right? Oops. And then in this case, 0 points at 1, 4 points at 0, 5 points at 0, right? So in this case, unfortunately, the thing is, the circled 0. That's the tricky part. So the tricky part is that right now, there's no edges going out to 0, right? But the thing is that there's also another node that has no edges. So you have this one, the -1, and so the thing is that now, let's say we process this -1 first. So then we give this a number. Let me use another color. So let's say for this cell, we give it number 1. So then in this case, and in this, because this 0 also doesn't have any dependencies, we also populate this as number 1. But now we have a wrong answer. We have a contradiction. We have a wrong answer. Sadness. Why? Because next we process this number. I'm changing colors again. Okay, that's too close. Yeah, because next we process this number, because now this number has no more outgoing edges because -1 is processed. And then now we have a contradiction, or just wrong answer, where this will be a 2 because we look at the 0 to -1, and well, and 0 to -1 will, the next number is a 2. But as you can see, this 0 is also this 0 is a 1, right? So that means that we're having some issues with our dependency graph. That it makes it not correct, and I didn't know how to handle this during the contest because it took me a while to think about it, because and this is a good lesson for myself, just to kind of think about how I did it. And the key thing to note is that, to be honest, I underestimated this part of the problem. I thought that the hard part of the problem is just the dependency graph, the topological sort, and stuff like that. But it turns out that this unique, and I thought that uniqueness was just like an edge case that I could handle with some if statements that I could fix later. I don't have to worry about it. Let me just focus on getting the code right, getting the code correct. But it turns out that this is not, as you can see, because during the contest, you can put, you could, if you try to do something greedy, like you could be like, oh yeah, you just kind of maybe change this one, right? Like maybe next we just go back and fix this one, or maybe you draw an edge here. There are a couple of different ways, but they're all just greedy. They're all heuristics. They depend on something that, you just reverse the order or just have something in a little bit different way. That's going to give you the wrong answer, right? So I knew that unfortunately, after I implement way too much, that's when I was like, oh snap, that's not good. But yeah, so about this time, during the contest, I was having a couple of Hail Marys where, like, okay, can I always go from like the smallest number to the largest number? I wasn't able to prove it during the contest. I only proved by ACA afterwards, but it turns out that you can, because when you process it in order, in a number order, no matter what, all your prerequisites are done. Because that means that, for example, if you process the zeros together, well, -1 will always have a smaller number and so forth. But so that's kind of the short story. But the only thing that is tricky is, but the only thing that's tricky with that is that you cannot just combine all the numbers together, because, for example, if you have another number, let's see. Let me change the color again. Let's say we have number 0 here, maybe. In this case, right, this answer is actually 1. Right? Let's say there's no more zeros in this case. This is not a 0, this is not a 0, this is not 0. Right? Then in this case, this answer would be 1. Or yeah. And from that, you could see that this group of zeros is 2, and this group, or this 1 0 is 1, right? So that means that you cannot just naively combine them and then, sorting or something like that. Though it turns out that you can close to it. So what happens is that what happens is kind of fun, actually, because let's get rid of these colors again and again. Oops, how did that happen? So let's say we get rid of these colors. Let's say that we get rid of these colors. 0, right? Let's say this is a 0 now, right? Well, okay, let's just say this is a 0. Ignore the blue, right? So that means that now this also has to be a 2, or at best a 2. It could be even higher number, right? But it has to be at least a 2. So let's say this we set at 2, and then this we set at 2, right? So now we draw this connection this way with the 2 zeros, and you can maybe even draw it this way if this was a 0 again. So this may so this is the kind of the insight that I had about. Unfortunately, I had about 10 minutes left in the contest when I made this insight, and I wasn't able to implement it very quickly because usually I am actually able to do this very quickly, but not this time because it is a 2-dimensional thing. So what ended up happening was that I just had some silliness around it. And also there was just like a lot of things with, and again, we have to be careful of how we do the how we kind of merge the connected components together, right? And what I mean by that is that is actually not a non-trivial, or it's not hard to implement, but it's something that you have to be careful about, because if you do the merging of these components naively, it could be n squared in the number of components or a number of elements inside the components, and then that may give your time limit exceeded. So you have to kind of reduce that to at least, you have to reduce that to as little as possible, and that's basically what I did. And then now I think we have enough to go over the code. Now, I haven't explained how I solved this yet, but that's basically the problem that is broken down. These are the observations that you need to make to solve this problem, right? And unfortunately for me, it took a little bit too long. But so basically now this is union find, a 2-dimensional union find. So I had some issues with this because just that I was a little bit rusty, because I'm so used to writing union find that in a certain way that I think I just didn't take account of the 2-dimensional aspect. And again, union find is also a prerequisite for this problem. I might do a separate video on union find at some point, but for now, let's just say that this becomes instead of a regular parent where your parent is just the index of the index of your parent is the index of the node. We set it to be the x and the y of the node. So that means that you still look at the parent of the node, but now it has a 2-dimensional aspect. And that's basically what I did. I've implemented, and because it is a little bit new to me, it took me a little bit longer than I would have otherwise. Maybe I could have finished it otherwise, but so that's why it took me an extra, I finished it about 10 minutes after the contest with a little bit of cheating. I took a look because the contest ended, so I just wanted to see if that was on the right approach, and I was. So I would have gotten it eventually during a contest, but I spent too much time on the other solution. But yeah, so this is a 2D union find. I just keep track of the parent, which is an XY component coordinates, and then I have to do some really fancy stuff to do the merging that we talk about, because you have all these numbers that you want to say, okay, let's say we have 2 1s, are they in the same group? Well, and now we have a connectivity problem, which is the same as actually Q3, where, okay, if A is connected to B, B is connected to C, so forth, right? A is connected to C. So we want to modify that in a way such that, let's say you have an entire matrix of zeros, right? Well, if you look at every zero, if you do a naive n square loop for every 0 against each other, that's your worst case. It's going to end up n to the 4th, or rows times columns times rows times columns, because you look at each element and then you're just looking at literally each element and then each element, right? So that's going to be n to the 4th. That's going to be too slow. So that is actually why I end up taking a long time as well, because I had to be smarter about that one. And so the key thing to notice is that you only, one is that you don't have to check every 0. You only have to check the zeros that are in the same row or the same column, and that's good enough. So that's basically what I did. This is, I don't know why this used to be something else. That's why it's called a queue. But basically this is just a grouping by the number. So this is, yeah. So for example, if the entire matrix is 0, then this would just have the entire matrix in X and Y. And then now for each number, I look at the vector that is given the number, and I sort it by the X coordinate first, because if you sort it by X, then that means that only adjacent nodes may only adjacent values would have the same X, right? This is, you may have to visualize it, but basically, for example, if you sort like 1 5 and 1 6, 3 5 or something like that, right? Well, only adjacent values will have the same X. So once you sort that, you're able to get that from n to the 4th to n squared log n. So that's basically what I did here. And once you do that, that is fast enough. And I do the same thing with the other dimension. I sort by the y coordinates so that I could check merging by the y coordinates, right? I even have some print statement that I left out here, and luckily it didn't time out for that reason. And now we use the union find to merge adjacent nodes. If they have the same X or the same Y, we do the same for column, so going up and down. And then now we have this thing where now I could have maybe done this another way, but basically for every node, now I group every node of the same value. So let's say let's say k is equal to 0. For every coordinate, we look at the parent and we just group them by the same parent, right? So what I mean is that, okay, let's say you have 3 different components. So A, B, and C is connected to 1. D, E, and F is connected to 2. Then now we have 2 connected components, and then we just wanted to put them in the list somewhere, and that's basically what I did. I put it in a default dictionary of a list so that I just keep track of all the parents and their children in the union find sense. Basically, given a set, get all the components and put them together, and then after that, I put it in events, because that's how I look at them. Because you can have multiple components and then just put them on events, and then you sort them, and then you process them in order, and that's pretty much it. This is a little bit weird, but that's pretty much the hard part, because now you know that and the reason why this works with, I call it events, but maybe it's not an event, is because this is the same logic as the topological sort or the dependency graph, which is that when you process a number and you process every number smaller than it, that means that there's no outgoing edges, right? By definition, because you're only drawing edges to smaller numbers, right? So you process all the numbers behind it. So that's how you can sort by the value, and it'll be okay. It's just that before we might have different components in the same section, right? So yeah. And then now this is a little bit tricky to read, because I solved this a little bit after the contest. But basically now we try to get the rank of an event. And basically the rank of the event is just that for each row, we keep track of 2 things. We keep track of what's the maximum number that we used or the last number that we use basically, right? And that's basically just, yeah, the last number that we use for that column or row. So that you can use it again. So that has to be rank plus 1, right? And also the last number that used at that number. I did that. So the reason is that, for example, maybe this is the visualization, but the reason I did that is that basically if the entire row is, the last number is a 2, then you want to use a 3. You also kind of look at your columns as well, or your rows and columns, so that you get the smallest number that is the next number from those 2 numbers. So that's why I have 2 for loops, 2 if statements here, and I also go through every node of the component to do that, because like going back to the visualization that we had before, basically we look at so let's say we're processing zeros. Okay, this is as undo as I can get. If we're processing zeros together, we try to look at, for each cell, we just look at what the next possible number is, and then we take the maximum of all those numbers, right? It's kind of intuitive, it kind of makes sense, hopefully, but that's what I do here. And so yeah, so that's just keeping track. And if it's the same number, then we use the same number. Though I think this logic that is not necessary anymore. I think it was from before, because I think this was a hack around components. Maybe I could be lying on that one, but basically that's the idea. And then after that, after we get the maximum rank, for each cell, we just update that to the rank, and that's pretty much it. And then we also update the rows and the columns to the new rank, and also the last value that we use, so that we can get the highest one. Yeah, because basically the new rank is either, if the last number uses the same number, then we just take the same rank, at most the same rank. Actually, this is not true. So I think we could just remove this, actually, because this cannot be true. Otherwise, this would be wrong. So actually, it's just that this case is actually no longer ever true. So that's why. So you can actually do something like this, which is way cleaner. Right, because basically these are the same numbers used, and yeah, and that's pretty much it. And then we update it afterwards, so that next time we do it, it'll be +1 from that. Yeah, so very hard problem. There are a lot of different observations to make, and for me, unfortunately, I like I said, I and you can watch me during the contest afterwards. It's really long, fast forward for it, but I thought that the unique case was an edge case, so I didn't really plan my coding and in my implementation for it. And also I had to do it with the naive topological sort, where I didn't do this thing of the defense on what we said. One of the observation is that when you process the numbers in order, in the value order, if you already did all the numbers more than it, then that number has to be the next number processed. So I didn't make that observation or proof until like a little bit later. So I ended up writing a lot more code. This is still a lot of code. This is 60 lines of code, but it is, at least much easier. At least it's doable during an hour. It's just that I didn't make that observation until much later on, about the edge case. So it's kind of cool. That's why I like this problem. Let's go over complexity real quick. So union fine, that's for now. I mean, I do path compression, so let's pretend it's all 1 for now. You can make that optimization with by rank if you really find that to be an issue, so that would be an up-solving thing. But this is just union fine. So I dedupe all the values in the same thing. So this number will have at most n square number of different keys, like with every cell in the matrix is different, and this will be n square. And then the other worst case is that they're all in the same one. So actually that is the worst case, which is that then this would take n square log n time. We kind of talked about that. So, and in that case, it will take O of 1. So this, I'm a hand wavy a little bit, but basically it is in between n square and n square log n is the worst case because each cell can only be sorted like once or something like that, and otherwise each cell is only in one thing. So let's say this is n square log n. It's a little bit hard to understand though, but yeah. And then we sort again, and then this is just straightforward. We look at each cell at most once. So this is O of n for this is row of O of n, and this is O of rows times columns times log of rows times columns, to be more precise. In terms of space, all we use is a matrix and a matrix for union find, but this is linear in terms of the size of the input, so basically linear space. This is a tricky problem to explain. This is a tricky problem to solve. So I wish I did this during the contest, but I didn't really understand how hard this problem was until later on. I think if I made one of those two observations earlier on, then it would have freed me enough time to do the later ones. So there are two observations. One is that non-unique numbers. So if you have duplicate numbers, you have to do this thing with connected components so that they all get handled at the same time. And the other observation is that in a way it's greedy in that instead of having an explicit topological sort graph of pointers pointing to previous, if we just sort it by the value, then it would have no out degree by the time we process it. That would have fixed implementation a lot enough that if I made one of those two observations, then I should have been able to solve it. If I made them earlier, I made them but really late in the contest. Yeah, so watch me solve it during the contest. Let me know what you think, and I will see y'all next contest, hopefully. Bye. Hey everybody, this is Larry. This is August 8th. So a week into the Leetcode August challenge. Hit the like button, hit the subscribe button, join me on Discord. Let me know what you think about today's problem. Rank transform of a matrix. I usually solve these live, so if it's a little bit slow, do fast forward, watch it on higher speed if you want. And yes, I say this every time because every time I don't, someone complains about my style not being the same as every other video, which in this case, you should watch other videos. It's fine. The world is a big place. Anyway, okay. So given where is the rank of it? What's the rank? How large an element? Okay. This is always a little bit weird because I think the rank is something in a matrix and linear algebra. So, yeah. Okay. Okay. So basically you're trying to process numbers at a time. I think there are a couple of ways I'm thinking about now. First of all, it always makes sense to pick the smallest number first. So I would pre-process. Yeah, so I would pre-process all the things to use, I think. Yeah, so I think sorry, I'm not being coherent because I'm thinking about it right now, and also, to be honest, I have a little bit of a sore throat, so I'm not as articulate as I am usually. But I think it makes sense that we always process numbers from the smallest numbers to the biggest. So my first thought is to just put everything in a sorted array and then process them one by one. And then once we do that, we can probably greedily just assign them, and as long as we're consistent with the minimum of the number, I think we should be good. So let's start doing it that way. There are a couple of ways we can do it, but yeah, I think one thing that I'm trying to think rather is that given the same number, do they always have the same rank? And I guess the answer is no, right? Well, it's even shown here that this is a no because no, actually that doesn't show anything. Hang on. Because I think so I'm trying to think of a case where that is the case. I don't know anymore, but let's say you have one. Right now I'm just trying to construct a case where I should say 10, where that is not the case. So what would be the thing here, right? Well, the answer for this would be the 1 would be the 1, the 2 would be a 2 for the minimal, and then the 10s. Well, this 10 will... okay, well, this is a bad example. Maybe 2, 1. Okay, let's try again. So we start the corner on the 1, and then the 2 will have a 2. The 10 on the top will have a 3, but this one should have a 2. This one could have a 4, and this one is a 5. So that means that even though they're 2 10s, they have different values. So now I'm trying to think about how to differentiate and whether the order matters. I guess the order doesn't really matter. As long as we do them all at the same time-ish. There are a lot of edge cases, and I'm trying to think. So another way to think about this is just with dependency graph, and then we basically do a topological sort of this entire graph, right? Because basically now we have a dependency and we're trying to do that. And to be honest, that was my first instinct. When we say sorting, it essentially is a topological sort. So then the question is, I think the topological sort is probably the better answer, because I think what I'm going to end up doing is I'm trying to do some greedy that's similar to topological sort, but not topological sort. So then there's going to be some bugs. To be honest, I was trying to avoid using topological sort, even though that was one of my early instincts, because I think it'd be annoying to implement. But maybe that's not true. Maybe so. So let's think about how to do it then. Given an n is 500, we have to be smart about this as well. So because that means that if you have each cell having 1,000 elements, one in each direction, that's 500 squared times 1,000 is way too much. Is that true? Yeah, it's probably true, right? Yeah, so I have to be a little smarter than that. This is a hard problem. I also vaguely have some recollection of this problem now, but yeah. Well, I think another way to represent the topological sort is by just looking at them instead of having every pair. So let's say we have a one-dimensional array, right? And let's say our array looks like just some random looking sequence, right? The naive way to do topological sort or to draw the DAGs is that 5 points to 1, 2 points to 1, 3 points to 1, and 4 points to 1, right? But you can actually just do them in order because you always have to anyway. So then you sort by 1, 2, 3, 4, 5. In that case, then we can maybe do the topological sort in a smarter way. By unlocking the next number. But wow, this one is just very annoying to implement in order. Like, it's not hard conceptually, it's just hard to implement it in a clean, fast way. So maybe I just need to grind it out. Okay. So okay, I think this is just implementation then. I think what I said here is going to be good enough. We just do a lot of sorting. We do a lot of keeping track. There are a couple of weird cases with the same numbers. That's the other thing that I'm worried about a little bit. Hmm. But yeah, it should be a small value. Okay. Yeah, this is an annoying problem. Okay, I'm only 10 minutes in. I'm still just thinking about the algorithms. But I think, to be honest, I think that's probably how I would do it. And then, yeah, all right. I think I just have to be good about it. Let's see. What is equal to length of matrix? Problem is equal to length of matrix of 0. And then each of these are 500s, okay? And then now for x rows, for each row, we want to, what do we want to do, right? This is a little bit, or maybe a lot messy, depending on who you ask. We want to say, let's see. So this is y. Actually, this is matrix of x, y. So we want to sort by this, and then also and then just correspond the value and then the column name, right? And then now we want to sort by it. We want to sort. So then now we can go construct. This is so awkward to implement. I'm trying to think about whether I can do this in a slightly cleaner way. I think there are ways you can do with list of lists, but it is yucky. Okay. Yikes. There's so many edge cases the way that I'm thinking about it though. Again, the edge case I'm thinking about is like numbers that are shared in the same way. Then how do you pre-process, or how do you process them at the same time? Or do you process them at the same time? Is it okay? Maybe it's just an implementation issue. Yeah, I mean, mm, maybe I could do it another way. Hang on. I mean, so the short answer is still going to be topological sort, but I'm trying to think about what's the best way to do it. Um, and yeah, hmm. I think that maybe that's all we need is this idea of. I mean, I think the two ways to do it. One is topological sort. The other one is the one that I keep on bouncing back to. Is this idea of okay. So I think we just need to figure out how to combine components. And when I say the word components, I'm thinking of union fine. And for example, this one, we will combine the two 19s together into one component so that we parse them together. Okay. So let's say we have and we only combine them into one component if they're connected to each other, either vertically or horizontally. So, okay. Whoops. Okay, so let's think about this. So, okay. So now we want to connect them all. Let's just start union fine. Okay. A list. So this is a list of the coordinates that we want to combine them into. Parent of. Oh wait. What am I doing? And then now we just want to find out a quick way to. Oh wait, I didn't finish actually implementing the union fine. Okay, so this is just union fine stuff. And then now we want to say now we want to connect all the components together. How do we look up all the components? Okay. I mean, we could create a graph. We can. So we can create a graph. What else can we do? Of all the spaces that are next to each other. But I'm just thinking about the case where, for example, if the entire matrix is all ones or something like that, then you're going to do something like n squared unless you're doing something smart. So I think you can use connect the components by just looking at adjacent elements. I think that should be good, right? Okay, so let's just say values is equal to list, and what we want to do here is so we have matrix xy, so we just put this. So now values just have all the matrix arrays here, and then now we can do a dedupe by the value. Okay. Okay. So now we have, for every value that has the same, we look at each value. So okay. So for v in values dot key, maybe this is a terrible name. So okay. So then positions is equal to values of val, and in that case, now we just have to look at so we want to sort by it doesn't really matter. We want to sort by both dimensions. So first we sort by the first dimension, and then now everything that's on the same row should have the same thing. Okay. So yeah, okay. This may be a little bit inefficient. We might think about it later. But okay. If p1 dot so if the x positions are the same, or I guess it doesn't really matter. Whoops, this is always going to be the same, but then we combine them. Okay. And then now we want to do it for the other dimension. Okay, so now we have these components. Right. Okay. So now we have all these components. Okay, so now we have all these components. Then what can we do next? Then now we want to put them in a now we just have to parse them together. together. Now we just have to put them into the same place, right? Okay, so sorry, I'm not being too articulate. This is a hard problem. I'm still trying to think it through a little bit. Okay, now we want things that are done, and then we just have a list of kind of events, say, list, and then we just go for it one more time. For p in positions, if p not in done dot add, oops, p and events dot add or append. We want to append the value which we sort by, and then the position which will give us the. Oh, this is not p. What we want is actually you find a p. Parent is equal to this. So if the parent is not done, we add it to the parent, and we add this. This is the sorting key. This is the value key. Oh, sorry. This is just the value, and this is the sort key, which is why I do it later. And then events dot sort. So now we have all these events. If this is a little bit confusing and hard to follow, bear with me. Or just fast forward a little bit. I will explain the thought process near the end. I want to get it correct first because this is a hard problem. Yeah. Okay, so I sort it. And now, okay, for event and events. Well, for event, which is the value, which we don't care about. And then the parent. Does this tell me enough? No, I think I need to do a little bit more. No, I need to look up the child as well. Children say. What a mess. So now for each event giving us the parent, we have a list of things here. So for child here, we will have the XY. So okay, so the best value that we can get is 0, say, and then now we try to, okay, so now we also construct row values, row next values maybe is equal to times rows. Is it, do we do 0 first or 1 first? Okay, so it's 1 base. So yeah, let's do, I don't know which one I want yet. And then for each child, we go, okay, we is equal to max of row next of child sub 0. We is equal to max of column next child 0. So basically now we're just trying to find the biggest number that we can do or need to take care of in its dependencies. And then here we want to set, and then now we do for child and children of parent again. Answer of child of 0, child of 1. I guess we can actually change this a little bit to make it a little bit clearer. So this is equal to v plus 1, and also we want to set this is equal to v plus 1. And by default, these should be the biggest. So, okay. Am I done? Don't know. Let's give it a spin. Just to, I've written too much code before testing it. Usually I don't, it's not something that I usually do, but, and this is wrong right now, but that's okay. Because there might be a lot of different components that just may be wrong. So let's kind of see, let's write a couple more test cases here. Actually, it's wrong, so we can do the other test cases later. Let's see. This is good. 1, 1, 1, 1. So this is good. This is not so good. So it thinks that the 3 should be 3. Why is that? It looks up. It should see 1. It looks to the right. It should see 0. So this should be 2. Dong, dong, dong. Let's debug real quick. Okay, so 0, 0. Yep, that looks good. 0, 1. Yep, that's the 2. That's good. Why is this 2? Dong, dong, dong. Oh. Did I mess up something up? So on row 0. All right, let's print this out. I think I messed something up, but that's okay. Learning is part of the fun. What am I printing? Okay, so 0, 0, now 1. Okay. And then after this, let's set it update. Did I mess up something? Oh, there you go. I did mess up something. Pretty okay. Hopefully that's it, but let's at least test the other 2 cases, and because this has the answer, we should be able to see something. Okay, so this looks good. Let's give it a submit and hope it's good. Probably come up with some silly mistake, but okay. Okay. Give me a second. This is an annoying problem. Actually, you know what? I'm not. Well, okay. If you're watching this here, this may not make sense, but in case you skip ahead and you're here, then just to give it a heads up, I'm going to put the explanation in the front. So rewind to the front or something like that if you're here, and then we'll kind of do the explanation there. But just to go, but while we're here, let's do the complexity real quick. So yeah, So for each unique value, we do a thing here, and then we sort it twice. So that means that for each, in this one, the sorting, and in the worst case would have n squared log n sorting. The reason being that, you know, that's the max number of value, and then you sort it by log n squared, and of course, because of the log, it becomes it becomes n squared log n. And let's just pretend that the unions are O of 1 for now. I know people are gonna give me pings about inverse argument function or whatever, but let's just say it's O of 1 for now. And in that case, yeah. And again, so it's the sorting, we have the same thing, but and everything will be dominated by this sorting. Here we just look at, you know, at first each cell. So each cell should appear in here once, and for each cell we just we look at it twice, once here and once here. So this is actually going to be O of n squared. So at the very end, the runtime complexity is going to be dominated by this sorting and this sorting, which is both possibly O of n squared log n. So that's your complexity right there for time. And for space, we do have one thing in the union find for each one. We also have a event for each item. So and set, I suppose, maybe. So in either case, it's going to be linear, which is n squared, because it's the linear in the size of the input. We only use a couple of instances here here as well. So it's going to be O of n squared for space. Yeah. That's all I have for this problem. The short answer is going to be topological sort. I did this topological sort in a funky way, trying to implement it in the cleanest way possible. I don't know that I did that, but there are a couple of ways to implement it for sure. So yeah, definitely experiment with it. And yeah, that's all I have for this one. Hit the like button, hit the subscribe button, join me on Discord. Hope y'all have a great rest of the Sunday. Stay good, stay healthy, to good mental health. I'll see you later. Bye-bye.